So in this video lecture, we'll be talking about frequency response and looking at how we take the transfer function and create a Bode plot from that and how we interpret the information from that Bode plot. So just so that we're all on the same page, let's go back to the system we've been looking at in our lab quite a bit, which is this servo-hydraulic system. And we have used this to come up with, first of all, the open loop gain and then close the system loop, meaning we put a controller in it, we feed back the information about where the position of the actuator is, and close the system. And from that, we're then able to develop this closed-looped transfer function right here, and actually the transfer function right there. So that's our closed-loop gain for the system. And now we want to be looking at that and saying, all right, let me actually put in some values, and if I happen to have this single integrator system, this K over S for my plant, and then just happen to have a simple controller here, just a proportional controller, we have this form in the very bottom where we've got our closed loop controller A over S plus A. So let's take a look at that from a frequency response perspective. So what do I mean by a frequency response? Well, we've got this closed loop system. So what happens if I send an input, meaning my reference signal happens to be a sine wave? So I've got this blue sine wave and I'm plotting it on the right so it looks like a regular sine. This is what I'm sending it as a command. But we know that especially as this sine wave gets higher and higher frequencies, the system will not be able to track it perfectly. So what is it going to do? Well, it is going to do two things. One is that it's going to start to decrease its magnitude, meaning that we're going to be going from 1 up here to some lower magnitude, and we typically call that magnitude M. So you'll notice that I'm scaling this sine wave by M. And we also get a shift in the frequency, or a phase lag. And so you'll notice that I'm going from a peak right here to a peak right here, and that difference right there is what we refer to typically as a phase lag, and you see it right there in the output. So by observing this from a physical system, in other words, if we send a sine wave to it and look at how it responds, we're then able to back out what the plant dynamics are. So how do we do that? Well, first of all, we express the magnitude and the phase angle of a function. And you'll notice here that I'm substituting in j omega for s. So this just allows us to look at what the magnitude and phase angle are for a variety of different angular velocities, or and in this case, omegas, which is the frequency in radians per second. So first of all, how do we find the magnitude of this transfer function? The magnitude here, and again this is a over j omega plus a. Well, first of all, I'm just going to be looking at the magnitude of the numerator, and in this case I only have real components, so I get a squared and the square root of that. And then in the denominator I have the square root, or the square of omega plus a, and the square root of all of that. So basically taking Pythagorean's theorem, applying it to this complex number, and then I get the form here of just a over omega squared plus a squared and the square root of that. Now, I also need to come up with the phase angle. So the phase angle, I first of all look at the numerator and say, what's the phase in the numerator? And in this case, I get an inverse tangent of the imaginary component. In this case, I have no imaginary component, so it would be 0 over a. And then I'm going to subtract from that the inverse tangent of the denominator. The imaginary component of the denominator is omega, and the real component is a. And so as I punch through this and I see, all right, I've got inverse tangent of 0, well, that is just a value of 0. And so we're just left with minus the inverse tangent of omega over a as the phase shift for this. So as we change omega, we can see how much the phase shift will change. So now I want to create a Bode plot, or a plot of how the system responds at various frequencies. So to do that, I'm going to say, what is my magnitude and phase angle at various values of omega? So let me start off by saying, what if I have omega, let's see if I can get that to work out for me. If I have omega much less than a. So let's say it's very, very small. And in that case, I'm going to look at my magnitude here and say, in the denominator, that omega squared term, that's going to go approximately to 0. And so I end up with a over square root of a squared, which is just a. So I get a magnitude of 1. Now I do the same thing for my phase angle, and I go to this inverse tangent, and if omega here is equal to very close to 0, I get inverse tangent of 0, and so I'm going to have 0 phase angle. All right. How about at the break frequency, where omega is equal to a? In this case, now I plug in omega is equal to a into this first term, and I get a in the numerator. I get a squared plus a squared in the denominator and the square root of that. So as I simplify that, I get 1 over the square root of 2. And then I do the same thing for the phase angle plot, and minus the inverse tangent of a over a, so 1, and that is 45 degrees, and notice it's a minus 45. And finally we say, what happens when omega gets very large? In that case, omega much greater than a. And as I plug in my numbers now in the denominator of my magnitude here, my a is really not going to be, this a squared is not going to play much of a role, so I end up with a over omega squared and the square root of that, so a over omega. And finally I do the same thing for the phase angle, and I get inverse tangent of a very large number, and that goes to 90 degrees, so minus 90 degrees for the phase angle. All right, so we have all the information we need to plug this into a frequency response plot, but one more step. I've got magnitudes here in absolute values. What I want is I want to turn these into decibel levels. And the decibel system comes from audio amplifiers a long time ago as far as how people heard various levels of sound. And it's just a way of coming up with kind of a log-based scale of basically expressing the magnitude. So you'll notice here on the right side I've got the decibel is equal to 20 times the log base 10 of the magnitude. So if I plug in a magnitude of 1 into this, I get 0 dB. So let me plot this dB right here. I get 0 dB. I do the same thing for 1 over square root of 2, and I get minus 3 dB. I plug in that same formula for a over omega, and now I get 20 times the log of a minus 20 times the log of omega. And I'm going to use that as a line that I'm approaching as an asymptote. So let me take all this information, move on to a little bit cleaner format, and try to create my Bode plot from this. So I've got all that information in that table on the upper right that I just created. And now I'm going to generate this Bode plot, and you'll notice first of all have my magnitude axis on the top here, and then I've got a phase angle on the bottom. So these are my two plots of the Bode plot, and I have this in terms of omega, and this is in units of radians per second in both of those. And you'll notice I've marked omega is equal to a here because this is the break frequency, or the corner frequency is what we call it. And this is an important value where things start to change for us. So first of all we say when omega is much less than a, I'm at 0 dB. So I'm starting off kind of here. And then at my break frequency, or where omega is equal to a, I'm going to be at minus 3 dB. And finally, I'm going to be approaching this slope here, which has, or this line which has a slope of minus 20 dB per decade. So it's going to be a line, something like that. That should be a straight line. And the slope of this is minus 20 dB per decade. And so now when I create my Bode plot, I know I'm going to start here. I'm going to asymptote to this supposedly straight line that I generated here. And as I do so, I'm going to get a Bode plot that looks something like this. That would be my Bode plot for the system. So fairly simple system to generate the Bode plot for, but allows us to start to look at how does the system lag as the angular velocity or the frequency increase. Now let me do the same thing for the phase angle. I'm going to get, again at my break frequency, I'll get a transition at minus 45 degrees. And then I'm going to asymptote to a minus 90 degrees. And so my plot will look something like this. So the purpose of this Bode plot is that we can now look at how this system is going to behave as I input various sine wave frequencies. And what we'll then do is we'll apply this in a chirp frequency where we vary the sine wave frequency and look at when does it respond well and where does it not. And we typically say when the frequency is above the break frequency of omega equals a, we usually don't want to be operating at those conditions because we have too much lag, more than 45 degrees, and too much decrease in the magnitude of this minus 3 dB. So we normally want to stay below that break frequency for our operation.